Let's, for the next about half an hour, we're going to talk about quality in databases. We're going to take the concepts we just talked about, what are good keys, what are good attributes, that sort of thing, and we're going to make a way for you to create good databases. There's two aspects of quality: effective data and efficient data. Effective data is a system that does what it's supposed to do. That you have accurately captured the business rules, you've accurately captured all the relationships, all the entities, all the attributes, and your database does what the customer wants. You have to go further than that. This pretty much is the database, the systems analyst's job, is to make sure that the database does what it's supposed to do. You have to go further than that, and you have to look at efficiency. And as I said at the beginning of the class, unless your customer has efficiency requirements, it has to be this fast. It can only be this big. For example, if you are building a database in an iPhone, and there are lots of databases in iPhones, almost all the apps these days have databases built in. You've only got so much space. You've got to make it fit in a small amount of space. If you're in an embedded system, we'll talk later about programmable logic controllers, where you're controlling a machine in a factory. If you've got a database in that software, it can only fit in so much of a space. Server-side stuff, it's less of a problem. So the other aspect of quality is whether it's efficient or not. And that's where it's small as it can be, but no smaller. And it's easy for a computer to do quickly. It's efficient. So the efficiency aspect of it is really the job of the database administrator. Somebody who's more concerned about the internals of the thing and how well it works, how fast it runs, how small it is, whether it's elegant or not. Now, you'll hear that phrase a lot, where someone says, this is a very elegant system. And I really don't know what that means. I know it when I see it. But it's like when you see a car, some cars are just better than others. You go into a house, and some houses just feel better than others. And it's a quality you begin to appreciate as you see a lot of houses. You imagine yourself living in them. Code and database design is no different. So some of these aspects of quality we can see, we can measure, we can say, well, there's fewer tables in this design than this design, or this design is 50% faster than this one. The other side of it is something you'll pick up over time, where you just look at one database design and you say, well, this is really well done. The person who was doing this was really thinking this through, and they set it up very well. It makes it easy to maintain, makes it easy to extend. That kind of quality is something, frankly, I can't teach you at this level. There are other measures beyond that kind of ephemeral elegantness. But these are all trade-offs. For example, today I'm writing this client. We are hosting this thing on a service called Heroku, which is a platform as a service. It's really cool. It's really sweet. I can deploy to a new server in one line of code instead of setting all this other stuff up. It uses a PostgreSQL database. Now later on I'm going to have to move that thing to someone else, probably to a service called New Relic. Sooner or later, if the company is successful, they'll have their own servers, and we'll be migrating it to another platform. So over time, my design of my database has to be transportable. At some point I may have to take it off this platform and move it to another platform. When I do that, the customer should not be able to tell the difference. They still get the same data. So you might find in your companies that they start on a Microsoft SQL Server platform, and later on they have to migrate to Oracle. That's a transportable database. It's a trade-off, because the reason those two databases are different is one is better at some things than the other one is. Oracle is optimized for certain transactions. SQL Server is set up to do certain things well. If you take advantage of those qualities, it makes it harder to transport it. The more specialized you make the design to fit its environment, the harder it is to move it to some other environment. So it's a trade-off you have to make. Personally, I know I'm going to be migrating off this platform sooner or later. So for me, transportability is an important thing. If you're in a company that has been an Oracle shop for 10 or 20 years and they have no intention of moving off of Oracle at all, transportability doesn't matter at all. You can optimize the heck out of it. A lot of things here. As a business systems analyst, one of the things you should do after you've got your biz rules and you've got your relationships and all that sort of stuff is you need to go talk to the IT department and the business people and say, okay, so what's the plan here? Are we going to be upgrading later? Are there other requirements? Do I have to optimize for different things? It has nothing really to do with what the customer wants. It has more to do with what's the business strategy going on. Okay, switch gears here. We've already talked about multi-value attributes. We've talked about situations where we have to take things and make them simpler. The thing we're trying to minimize here is redundancy. We're trying to eliminate redundancy. And as we talked about, having redundancy makes things inefficient. It also makes things ineffective. If you have redundancy, sometimes you don't know which thing is true. So we're going to try and reduce redundancy or eliminate it. Now something that is new in this presentation, in this discussion, is something called dependency. Now we've already seen a dependency that is in every table, and that is the record depends on the primary key. That primary key is unique. I can always find the record if I know the primary key. So I'm not saying that dependency itself is bad. Dependency is part, certain things depend on other things. Being able to find out your name depends on me knowing your genome. And that's what I mean by dependency. However, there are times where dependency is not good. So let's take a look at that. So here's the deal about primary key dependency. When you review this thing, this is where you hit. Now, we've talked about primary keys that are composites. So let's say you didn't have a G number. And I had to figure out who you were as an individual by taking your first name, your last name, your address, I don't know, whatever else I could find out about you until I could come up with a combination of attributes that uniquely identify you. If I were doing my database that way, those set of attributes would together form a primary key. It's a composite attribute. It has multiple values. We've already assumed that has its own problems. So if we're using those composite keys, then we may find ourselves in a situation where only part of the primary key is really important. I'll show you some pictures of this in a second. The other kind of dependency that we run into is called transitive dependency. This is a situation where one part of the data depends on another part of the data that's not the primary key. I've got connections within my database that just are sticky. It's as if, when I turned on the headlights, I had to have the spare in the trunk. There's no real reason for those two things to be connected, but the way the car is designed, I have it. Now again, dependency is not always bad. For example, to turn your lights on, you have to have the car, in modern cars at least, you have to have the car on. If you turn the car off, after a few minutes the lights turn off. The lights depend on the engine. Sometimes that's a good thing. However, with your emergency flashers, for example, you don't want them depending on anything. You want to be able to turn them on, turn them off. You want some parts of your system to be completely independent of everything else. So let's see some examples here. Hope you can see this from here. So we're going to start taking a look. We're going to use, for an example, an invoicing system. We saw this Tuesday. Let's take another look at it. So in this invoicing system, I'll use my laser pointer. I've got customers. Each of them has a number, and I'm going to assume that this customer number is the primary key of the customer table. I've got invoices. I'm not showing you, well, I've got a bunch of invoices here. 157, 1057, 1058, 1059. Each one of them has multiple line numbers. So I've got line number 1, line number 2, line number 3. These are the invoice of 1057. Each of those line numbers has one product. There's some sort of product code. I don't know what this means. This is the really bizarre thing about this example. I don't know where this came from. But we are selling them F-16 fighters. We're selling them B-777 transports. And we're selling them cruise ships. I don't know who this company is. These are big ticket items. Now, for each one of these invoices, for each one of these lines, for each one of these products, I am also storing the customer number here. So this invoice is going to this customer. So tell me what's wrong with this table, first of all. This bottom table. I've got a bunch of redundancy in here. So identify some of the redundant elements in this table.
So you can pull all the cruise ships out and put them on the table.
Okay, well I'm not sure. No. Okay. Products are not one of the things I want to pull out of this table. Other ideas?
Customer.
Customer number. As far as I can tell, every time I've got an invoice, I've got one customer. I don't have any invoices. 58 is one customer. 59 is one customer. 60, all one customer. I've got this dependency where customer number is redundant. If I know the invoice, I don't need to know the customer number because it's always the same. I can pull those things out. So here I've got one attribute that depends on another attribute. See this little arrow thing up here? And that's called a transitive dependency. That's an aspect of our table that indicates we can do better. That arrow is an example of something called a data dependency diagram. We don't have, in ERDs, we're just showing relationships. Now we need another kind of diagram that shows us how things relate inside a table. And we're going to use this thing called a dependency diagram. Data dependency diagram. Let's take a look at one. Unfortunately, these arrows are tiny. Let's pick this thing apart. So our dependency diagram are these little tiny arrows. There's an arrowhead, there's no arrowhead. There's an arrowhead, there's no arrowhead. Transitive dependency is shown when you have two attributes within the same entity that depend on the one attribute depends on the other. Partial dependencies is a situation where I've got this primary key, it's a composite primary key. Two attributes that together form the primary key. But in this situation, the customer number attribute only depends on one of those. It's kind of wacky. I don't like that. So let's take this diagram and interpret it. This upper arrow means is that together, this invoice number and this line number together form a primary key for this product that I'm selling. Pam, I apologize. You were right. If what you meant was that I don't need this column if I got this column, you were exactly right. I don't need both of these columns. But anyway, getting back. feedback, just wanted to clear the air there.
Wasn't what I meant, but thank you.
Oh, well then, I withdraw any apology whatsoever. Okay, so the first thing is, all of these attributes have to do with the line number, but there are lots of line number ones, so I need both the line number and the invoice number to uniquely identify these attributes. That's why I say I've got a composite primary key. And that's what this means, that these two things together, that each one of these attributes is dependent on the combination of these two attributes. A lot of times in computer diagrams you have to take the arrow backwards. So when I say this guy depends on that guy, I'm following the arrow backwards. Don't ask me why this is true. There's probably some mathematical reason for it. I don't know. The other one is, as we said earlier, the product title and the product code, it's redundant. This product code is always an F16. There are lots of different forms of F16, but here I got NV41, NV41, they're both F16. T40, T455, T455, they're both B777. I don't need to know the name of this product if I've got its code. So I've got this transitive dependency inside. And like I said in the last slide, if I've got an invoice number, I know the customer number. I don't need to have that in the table. I've got a partial dependency. When you start from scratch, and you have a database and you're working it from scratch, you usually avoid these things because your ERDs show you, oh, this thing is only related to this thing. But a lot of times what happens is over time people add things. And they say, oh, we're going to do this way. Or what also happens is you have a systems analyst that has fuzzy finger. Or you have a customer that says, oh, no. I have to have both the product name and the product code in the table. They're leaping to solution space before you tell them, well, I can show you a report. No, they have to be in the table. So these are the ways these kind of errors can creep into a design, either over time as people upgrade the design, or through listening to the customer too much, or through just fuzzy thinking. The question is, now that we've recognized them, what do we do about it? We use normalization. We take these dependencies and we try and extract them out of the database. We take the redundancies, we try and extract them out of the database. We take all of those multi-value attributes, we try to make them single value. We take all of those composite attributes, we try to make them atomic. Now when I say normal, I don't mean normal like every day. I don't mean normal like something you'd see if you were normal, as in not aberrant. I mean a mathematical sense. And I'm going to just touch on this. The reason I'm going to go into this, even though it doesn't matter much to you in terms of doing this, is when someone says, you know, I want to go to the third normal form. If you're a database geek, or you're talking to database geeks, third normal form is a phrase you've got to know down. You've got to understand it, and you've got to be able to sling that term like you know what you're talking about. Or else no one will believe you're part of the in crowd. And that's part of what we're doing here, is making sure you folks sound good as well as are smart. So do you remember in geometry class, for those of you who have taken geometry class, this symbol for 90 degrees, a little square down in the corner. This is a special angle. 90 degrees is special. If you remember Descartes, I think, therefore I am, one of the things that monk did for us is he gave us the Cartesian plane. The Cartesian plane is where you've got, x on this and y on this one. And if you have a function that says, oh, let's see, disks fail when they're new. So if I put time on this axis, and I put fail on this axis, then when something's new, it fails a lot, but then after a while, the failures stop. They kind of burn in and it's okay. A lot of new cars fail the first time. When you first get it, a lot of things fail because it's the first time you've ever used that car. Car is great for a while, and then it gets old, and then it goes up. Fail increases. This is a function. This is a function. Function, and a lot of times you'll see that written as x is a function of y. What does that mean? If I know what y is, or actually this is backwards. Y is a function of x. If I say my car is 3 years old, then your insurance company says, well, then you're a good risk, because it's unlikely your car is going to fail. If you say my car is 15 years old, then your insurance company is going to say, no, we're not going to insure you because the likelihood of failure is so high. So what this function gives you is the way to predict something based on something else. Okay, we're moving quickly through here. There's two forms of function that one thing doesn't depend at all on the other thing. And that's a function that looks like this. Here's one of those functions. This is a situation where x is always the same. You've got a car that fails no matter how old it is. It always fails. That's one kind of function where the one variable is independent of the other. The other kind of function is in the other direction, right? All cars fail the day after the warranty expires. So for these cars, failure happens on a particular day. Why are these functions cool? Because they are normal. They are normal to the axis. This variable is independent of that variable. So when I say something is normal, another word you'll hear geeks throw around is orthogonal. Oh, that problem's orthogonal. What they mean is that's unrelated to anything else. And that's where normal comes from. When we use a normalization process, we pull factors, we pick apart dependencies, things that depend on each other, and we make them independent. We make it so that one piece of our database no longer depends on another piece of our database. We take it and we make it independent. So if we have a car, and I don't know if you've ever had a really old car where you turn on the wipers and the lights go out because they got some sort of short in the system, or you can't turn the engine on unless you've got the rear door open or something weird like that. You've got some weird dependency going on there. Software is full of this stuff. If you have software, I don't know how many times you have to go to one piece of the application and turn something on before you can go to the other piece and turn it on. It happens all the time. This normalization process removes those situations. Back to the point. What's the bottom line here? Normalization is something mathematical. Doesn't mean it's common. There are three forms that we're going to worry about. You are responsible for knowing the difference between these three forms. Okay? You guys go into databases. In 5 years, I want to come talk to you and hear you rant about normal forms. Because they'll be important to you. When you go to conferences, you'll sound like you know you've got your act together because you can sling that shit like nobody else. For right now, let's just move forward. So, the first normal form is simply I got PK integrity. And every cell has something. And that value might be null. So what have I done? I've removed all of my multi-value attributes. I got PK integrity, and I've removed all of my multi-value attributes. I got one and only one thing in every cell. I might still have dependencies, I might still have other problems, but at least I fixed these two things. I do have PK integrity, I do have PK dependency, and I got no multi-values. experts that will disagree with me on that. Now, here's a key concept. To get to second normal form, I have to meet all the requirements for first normal form. So I have to have PK integrity, I have to have PK dependency, I have to have no multi-values. Then I also have to have no partial dependencies. Now this is kind of like the difference between grade school and high school. When the school system is working well, in order to be in high school, you have to meet all of the competency requirements that you got in grade school. It doesn't mean you're still in grade school. So when you're in second normal form, it doesn't mean you are also in first normal form. It means you're in second normal form. It's just that second normal form is a lot harder to get to than first normal form. Third normal form is we layer on one more thing. I have to meet all those requirements. This is like grad school. I have to make it all the way, or it's like college. I have to get all the way through grade school. I have to get all the way through high school. And I have to be no transitive dependencies as well. So if you think of it like a table, let's go back through it. So first normal form means I've got PK integrity. It means I've got atomic values. Is it atomic? No, it's single values, excuse me. It means I've got PK dependency. What are the other two? Partial dependencies. And transitive dependencies. I do not have partial dependencies. Well, I do have them. It's not a requirement for first normal form for me to eliminate. So I have to eliminate these three. I have to have these three qualities. But to get to second normal form, I have to have these three, plus I have to have this one. I have to have eliminated all my partial dependencies. To get to third normal form, the nirvana, the holy grail of this class, I have to have all of these qualities. Okay? Why do I go over this in such detail? Historical value.
Will there be times where that's not possible? Like in the invoice one is kind of what I was thinking. I mean, invoice and line number, you have to have that composite key. So, I mean, is there times where you don't really have a choice?
Yes. Well, let me put it a different way. You can always get to third normal form. Like for that composite primary key, I would just define my own primary key column. That way I would get this, and I would get this. Now, but, because you can't always do everything in a business situation, in academia, perhaps you could have an ideal database. In a business situation, if you go in and change a database at some fundamental level like this, it means a lot of work. And you might not have the budget for it. You might not get permission to do it. For many other reasons, it might not be a good idea. So you may have to live with first normal form or second normal form. The other reason you might find yourself is after you go through and make it effective, make the database effective, where it is beautiful, have you factored all this stuff out and in third normal form, it may be slower than a dog. It may be horribly slow. And the way you speed it up is by taking all those, say you got 1,000 tables. I don't care how good your database engine is, you got 1,000 tables, you got to go look up a lot of stuff. So you take those tables, you put them back in. Or sometimes you'll take a couple tables and combine them for deployment, because you know you're going to be querying all those attributes at once. So you put them all in the same record so that the database engine can pull them out really quickly. So there's two reasons why you might not make it all the way to, you might not end up all the way at the highest level. One is you might run into some other real world constraint that prevents you from getting there. Or two, it may not be as efficient as possible. And you should always go as far as you can so you understand the problem. But you may have to back off, and that's called denormalization. As you go through this, as you identify these problems in your design, and you pull stuff out of the tables and you redefine what the tables are, you really need to go back and update your business rules and update your ERDs. One of the big problems in software development, one of the big problems in IT development, is the documentation doesn't match the system. And you'll get a lot of pressure over time to just ship it and not update the documentation. In fact, I'm talking to my subcontractor today. He's written all the code. It works. But some of it is not documented. So his job now, and I'm paying him to do this, his job is to go back and add documentation. Why? Because I'm still having that conversation with my client. I still have to be able to talk to my client in these other forms. And when he says to me, oh yeah, this piece doesn't relate to that piece, I can still be using ERDs for that part of the conversation. There'll be a lot of pressure not to come back and update all of the pieces of your design. But make sure it all hangs together. Similarly, if someone comes along, you've got your ERDs, you've got your biz rules, you've got your tables, you've got your relationships, all that stuff, and then someone comes along and changes an ERD, says, oh, no, we're going to handle invoices differently. You got to ripple that change all the way through. And then when it changes your tables, you got to look at your tables and say, ooh, that made it inefficient. That made it ineffective. I'm going to renormalize this thing. And I'm going to look at this whole thing. Again, like I said earlier, sometimes your customer doesn't care. They just don't care if it looks good inside. So what you have to do is you have to get really good at this and you have to be really quick so that they never notice. And in fact, what you'll find over time is that when you start designing databases, you'll already be thinking in third normal form. You'll never create a table that doesn't have these attributes, that doesn't have these characteristics. Because you know it's just making work for yourself later. Like, this is why I keep harping on this thing. Just let your database create your primary keys for you. And even if your customer says, we got G numbers, we don't need primary keys, you say, fine. I'm going to just go ahead and I'll have my own primary key. It's because I know I'll never run into this problem. To me, a G number is just another attribute. It's not a primary key. Because then if the business messes with G numbers, my database doesn't get hurt. Okay. We're going to go through an example of how this plays through. And then we're going to stop. I'm sorry this will take a little longer than I expected. But we're going to take a look at this example of our military industrial complex company that sells airplanes and cruise ships. And we're going to fix their tables. This has all three problems. So in fact, let's see, does it have primary key integrity? Yeah, it does. This composite primary key is unique for each of these line items. Or it uniquely identifies a line item. Does it have single valued attributes? Yes, it does. I don't have like product code comma B77 in one cell. So I'm good here. Does it have primary key dependency? Yes, it does. That's that upper arrow. So I got partial dependencies, yeah. I got transitive dependencies, yeah. So I've got a table that is in first normal form. So let's fix this guy. So the first thing I'm going to do is I'm going to work on that composite primary key. So I break it up into two pieces. And I realize now I can just take that invoice number and I can associate it with customer number. That's all I need to know who my customer is. And I've got a sweet little table that's already in third normal form. I don't need the line number in that table because nothing in this table depends on the line number. And I've pulled my customer number out of my line number table. I've taken it out of here and I put it up here. So the old one looks like this, where I had this partial dependency. And the new one, because I've got that separate table, makes it simpler. Simpler in the sense that it's easier for a computer to understand. Yes, there are two tables now, but each one is simpler than the one I had before. All right, so what's the next thing I'm going to deal with? I got that transitive dependency in here, where I got product code and product type. They're redundant. I don't need both of them in that line number record. So again, I'm going to extract the product title and put it in its own table with product code. Product code will serve as my primary key. I can always look up the product title from the product code. This is a sweet little table. It's in third normal form to begin with. It's very simple. And bingo, bango, bongo, I have gotten that out of my table. I've gotten that partial dependency and that transitive dependency out of my table. So now my line number table is now third normal form. It's got no partial dependencies, no partial dependencies. It's got no transitive dependency. So it's in third normal form. Again, this gives me the willies, so I probably clean that up. How would I clean this up, by the way? What would I do to make this so that this table had a atomic primary key? Any ideas? Oh, come on.
Auto numbering. Create another.
So create on my own primary key field. And then what does this invoice number become? I still need it. But it points to another table where I just have invoices listed. In fact, I've got the beginning of that table up here. So I would put a primary key up here, and put a primary key up here, this would be a foreign key here. That way now I don't have a composite primary key down here. This is a foreign key. This example shows you using actual data from the system, the invoice number, the product code. These are being used as primary keys, and that's their intention. In the real world, though, at Tektronix, for example, while I was there in 2003, they had hundreds of thousands of product codes in their database. They have been in business for 60 years. They've shipped a lot of products. A lot of those product codes were the same as other product codes. Because over the years, people forgot and they reassigned product codes. So they actually spent, I think, 4.5 man-years weeding out redundant product codes because it was starting to mess up their database. And then they went to work on their inventory database where they had part numbers, because every product has thousands of part numbers. Yikes. So managing your product codes and your invoice numbers and all that sort of stuff, it's a science all by itself. So our examples are necessarily simple. If you walk into a job interview and they say, Should I use a product code as a primary key? You can say, well, sure, that would be the simple way to look at it. But that will run you into problems later on. So I would use an auto-numbered, auto-generated, guaranteed to be not null, synthetic primary key. Okay. So we've already seen that we don't like first normal form databases because they're sloppy and dirty and nobody invites them to parties. We kind of like second normal form databases because they've got more data in each row than they need to, which makes it efficient to pull a lot of data out of them quickly. However, it makes them hard to update. So if you have to do transactions quickly, if you have to make a lot of writes, they're not always the best deal. But here's a situation where you may not want to go to third normal form. If you're constantly doing really complex queries, it can speed it up to put more stuff in each entity's row. I don't think this is in any exams or the quizzes, but it might be. And if you look up on the web, So Help You Cod, you'll find the world's only database joke.
So help you cod?
So Help You Cod. So Help You Cod.
Like fish?
No, Mr. Cod.
Oh.
Mr. Boyce is the guy who invented normalization, and Cod came along later. Anyway. Yeah. This is redundant. And we're going to leave this as an exercise for the observer. So, I hope I have beaten the heck out of normalization. I hope you never have to deal with it. But for those of you who are interested in a career in databases, this is fun, and it's like killing tanks from the Marines. It's fun and easy. The rest of us, it's hard and scary. But if you're a database analyst, normalization is fun and easy. Where the heck did that metaphor come from?